Okay. Hello everyone. Do you have any questions about the last times? Okay, so let us start maybe a relatively new topic. It will be about different problems inside and outside the unit disk. So what kind of problems? The basic setting for all these problems will be the following. We'll have the unit disk uh, radius 1, and we will have some function on the defined on the boundary of this disk. So this is called D, and we have some function f of phi. And we always suppose that it is such a function that can be expanded into the Fourier series. So the meaning of this function will be that it is either some a boundary value or some jump. So we will see what kind of problems we can formulate. So in the problems, so there are of course more complicated problems, but today we will study the Laplace equation and its simplified version. So the first two problems are for this Laplacian, which is 4 dd bar. And the first problem is to find such a function inside this unit disk so that its boundary value coincides with phi. Um, find such f of z bar, and that a dd bar of f equals to 0. And this z is inside the unit disk. So a dd bar of f is 0, and the boundary value of this function coincides with. Oh, sorry, I've used the same notation, but maybe let me call this function u of z bar. F of so u of e to I phi, its boundary value should coincide with f of phi. And the second problem for the same equation is to find so everything is the same, but now z should be in the complement to this disk. So z is in C minus d, and we also ask f of oh, should we ask this no, we don't ask anything else. This should be fine. Okay, so there are such kind of problems, and also there are modifications of these problems when we ask for some special behavior of this function at infinity. So there can be problems like 3 and more, then So in this problem, we say that f of in infinity equals to some constant. Maybe we can say that it is less than infinity. But there can be also problems where we ask the same, like z is in the complement, but the asymptotics of this f is something like f of z minus z, f of sorry, again, it is u. So u of z minus something like c z plus z plus z bar should be should go to 0 when z goes to infinity. Should be should be less than infinity. We can formulate problems of this kind. No. All these conditions are the same, but we add, we change this condition about z and add some asymptotics at infinity. So actually, as we know, this Laplace equation is invariant under the transformation z to z inverse. Actually, under any conformal transformations given, some transformations given by holomorphic functions. So if we do such a reflection, then such conditions at infinity will turn into some singularities at 0. So this function will not be holomorphic inside the unit disk, but it will have some singularities. But people formulate these problems in such a way because it has some physical meaning. For example, such condition corresponds to some constant velocity at infinity, or to some constant electric field. So, for example, it can be a problem about some metal surface immersed into a constant electric field, or about some cylinder falling in the water. Yes, so there are such kind of problems for Laplace equation. So, are there any questions about that problem? Yes, you fix some function there. Okay. So it is for this operator, and here, as always, we can separate this problem with trivial conditions of infinity and problems with non-trivial conditions on the boundary, because the difference of two solutions will satisfy this equation with boundary condition, like 0 here and something at infinity. So these problems are independent, always, for linear equations. So just some upgrade of the original problem. So, and another set of problems which I hope we will study is for simplified operator, and namely for d bar, just for 1/2 of this Laplacian. And so what kind of problems we can study? So we can so since it is d bar, we are interested in functions that are holomorphic. In a sense, we want to have d bar u equals to 0, d bar u of z bar maybe let me write simply u of z equals to 0. And then maybe better to write it is in the overall condition as the bar of u is z is 0. And here we choose some conditions. One condition is to say that we know we want to find this u of z in the vicinity of the boundary. So we are asking literally for this u of z, u of e to the I phi equals to f of phi for, oh, yeah, something like this. So we are looking for, so it's literally the same problem, but we'll then understand the meaning of this problem, because we can ask this at the boundary. So it is such a function that coincides with f on just a boundary of this disk, and then the question is how long we can continue it inside and outside, and this will be encoded in the behavior of the Fourier coefficients of f, and it's actually an example of a non-well-posed problem. So it is the problem about analytic continuation of some function that was restricted to a circle. So it is kind of expected, because it is the inverse problem to reconstruct the holomorphic function from its Fourier series on one circle. So another problem is to fix the real part of this function, real or imaginary part on this boundary. So here u of we will find u of z with z is somewhere in some domain, which will be found later. So another problem is to ask that a real part of the u of e to I phi equals to f of phi, and reconstruct the whole function and its imaginary part, for example. This will be a well-posed problem. And another well-posed problem is the following. So we look for the function which is holomorphic in the whole plane C without this boundary, without without the boundary of this disk. And on this boundary, we have some jump condition saying that u of u of e to I phi plus epsilon minus u of e to I phi minus epsilon equals to f of phi. And also another condition that u of infinity equals to 0. And this is a well-posed problem, and it is called a Riemann-Hilbert problem. Maybe that's all, because it seems that Okay, I cannot remember any other problems. Also, there is another problem, which is the generalization of this one. So probably I will tell about this. There is a problem analogous to the Poisson equation with some trivial right-hand side. It is called Debar problem. When we study the equation, Debar of u equals to rho. So it is a kind of a first order a version of the Poisson equation. And this is some simplified version of this Debar problem. So I hope you will also study it. So, do you have any questions about this? Uh, so this Debar problem is not necessarily in the disk. No, we can study it in the. Yes, we can combine this with all these conditions, but we can also look for just a holomorphic function. No, not a holomorphic function, but function satisfying this condition going to zero at infinity. So. Mm-hmm. Yes. But yes, we can also combine it with problems like this. In any case, we can subtract the two problems and get, for example, this problem with some simple boundary conditions. Yeah. But maybe the best problem to combine with it is something like this, because there are really problems with the same of the same kind. Because this jump condition can be written as the Debar problem with on the right hand side concentrated on the boundary. Everywhere except this boundary. And this boundary we have jump. Sorry. Thank you. Yes. So this, I don't know, maybe something of this might look complicated, but actually all such problems can be solved simply looking at the Laurent and Fourier series. So let us maybe start solving them one by one. So is it okay? Or do you have some questions? Okay, let us start with these problems for Laplacian. So the first problem is to find some function that is a harmonic inside the disk and it has some boundary conditions. So boundary conditions are there, and let us just guess some formula for this function f of z bar. Uh, uh, Let us write it as a0 plus, let me maybe write here immediately f0 plus sum from n equals to 1 to infinity fn z to the n plus sum for n equals to minus 1 to minus infinity. Maybe let me write as before, from 0 to infinity f minus n from 1 to infinity z bar to n. Oh, thank you. Yes. Oh, I'm just writing the answer because so it is super easy. We know that z is r e to I phi, and we put r equals to 1. So z is e to I phi, z is e to I phi, z bar is e to minus I phi. And when we write this series, we can also write it in this polar coordinates. So we can write it as u of r e to I phi, r e to minus I phi is f0 plus sum from n equals to 1 to infinity fn e to I and phi r to the n plus sum this sum f minus n e to minus I and phi r to the n. So we see that if we put r equals to 1, we recover precisely our initial series, and moreover, if this original series was convergent, then this series is convergent as well, because absolute value of r is less or equal than 1. Well, just r is less or equal than 1. So this problem is well posed. We can fix any boundary condition and find some function that is harmonic and satisfies these boundary conditions. So the answer. Are there any questions on this? So, and, as always, so if you have some problem with special boundary conditions, for example, the boundary conditions that have just a few terms in this right hand side, or this expansion on the right hand side looks like a Taylor expansion of some function, then you can just use this formula, and that's all. But if you want to write the solution for a generic function using the Green function, we would like to sum the series into the kernel that defines this Green function. So namely, we would like to write this for arbitrary f, or maybe how to say it better. We can write the solution for delta function on the right hand side, or we can say that this fn's equals to 1 over 2 pi integral from 0 to 2 pi f of theta e to the minus I n theta d theta. We can substitute this, for example. So then this u of r phi will equal to the integral of d theta over 2 pi f of theta f of theta plus another integral. So pi we have the sum, sum of integrals, and we can combine it under under a single integral. Ah, yes. Sorry, I missed summation from sum from 1 to infinity. So it will be the integral d theta over 2 pi f of theta. And now we just need to compute this geometric progression. Maybe we combine this one with one of them. So it will be 1 over 1 minus r e to I phi I phi minus theta, and that one will be r e to I theta minus phi, probably divided by 1 minus r e to I theta minus phi. So is it okay? Where? Plus. No, but f of theta is in in all these terms. So it is something that should be integrated with the green function. So now we just need to combine all this together. So it is integral d theta over 2 pi f of theta this times this. And here we see that when we start multiplying this, and there will be contribution, there will be 1 minus this exponential, and this will cancel, this exponential times r will cancel with such contribution from this term. So the only term that survives will be this one multiplied by this. So there will be 1, and there will be this term multiplied by this, which is r squared. So it will be 1 minus r squared. So is it fine? So and this way we find that this is the green function corresponding to this boundary to bulk problem. So this green function, that is a function of r pi the theta, is 1 over 2 pi 1 minus r squared 1 minus r e to the I phi minus theta 1 minus r e to I theta minus phi. And it can be written in different forms. So we can, for example, remember the definition, or we can introduce some definitions like theta equals to that and there is some variable w on the unit circle, which equals to e to the I theta. And you can write this in terms of such variable. So this will be 1 over 2 pi 1 minus r squared. So these two terms are conjugate to each other, and this term equals to 2 z over w. So we can write it like 1 minus z over w squared. Or so using the fact that absolute value of w is 1, it is like this. So another option is to write it in terms of real functions like this. One plus r squared minus 2r cosine of theta minus phi. I just wrote this formula to show that this denominator is the square of distance between the point inside this disk and a point on the boundary. So, and this formula can also be written like this. So it's kind of squares of two vectors, and this is their scalar product. So, so we have such a green function, and so are there any questions about this computation? Using this green function, we can write that a u of r e to the I phi equals to the integral over from 0 to 2 pi d theta over 2 pi g of r phi theta sorry, r phi f of theta. So, so hmm? Hmm? Yes. Thanks. Mhm. For example, there is an exercise to check that this green function becomes a delta function when when absolute value of r is 1. So that we actually cover this boundary value. So, any questions? Oh, but there is another approach to the same problem, and it's actually related to this formula. So this approach is the following. Oh, do you remember the formula for the green function inside this unit disk? So, namely, how to write g of z bar w bar. So, what parts does it contain? No, this formula is for the gain function of this problem. So let me maybe introduce some different name. So uh, let us denote this gain function by g hat. So this function, this gain function was from boundary to bulk, and there is a bulk to bulk gain function which solves this problem. So Laplacian of u of z bar equals to rho of z bar u of z bar in the integral over the internals of the disk g, let me call it g hat, z bar, w bar, rho of w bar d2w. And so there is this equation, and there is also the boundary condition. U of e to I phi, e2 minus I phi, in a sense u on the boundary is 0. So there is this gain function that solves this problem. So basically, it is a solution of this equation such that mm, how to say it? So it is a solution of this equation with delta functional right hand side. With a single charge placed at the point W, and with zero boundary conditions. So we computed it at some moment using a kind of method of images. So can you try to reconstruct at least some terms of this gain function? Oh, first, it is two-dimensional space, so it behaves algorithmically, right? So it has. So the first question is where is its singularity? Mm-hmm. Yes. Uh, Logarithm has singularities both when its argument is 0 or infinity. And the gain function in 2D behaves like 1 over 2 pi log of z, absolute value of z. So it's mm-hmm. Yes. But there was one more term that makes this function 0 on the boundary. So how to reconstruct this? Oh, but who is e to the I phi in terms of w? So uh, no, we have only two variables, z and w. Mm, oh. So some hint is the following. If we are looking for if you're asking it to vanish as a function of z, then we can write that this z minus w, absolute value of z minus w, is the same as absolute value of 1 minus w over z, because absolute value of z is 1. But again, since absolute value of z is 1, it is the same as 1 minus w times z bar. And this is the idea. So these functions are different, but they coincide in the unit circle. So we can simply divide by this function. So 1 minus w z bar. And the picture for this is the following. We have this circle, and we have some charge at radius r, some plus charge at radius r, and minus charge at radius 1 over r. Is inversion. Yeah. So we have this gain function. Are there any questions about this? And now we want to compute its normal derivative, because a normal derivative when its argument w goes to a boundary. So because we studied these relations between different gain functions and found that formulas like this should hold. So so this is in G hat. So some conjecture is that, or not conjecture, but a formula that we obtained at some moment, that this G of Z, let me write it like Z and theta, should be the normal derivative of this G hat, normal derivative in W of G hat. Z bar, W bar. So it is the same as the radial derivative. So we can write that it is d in dr of this G of zw at absolute value of w equals to 1. So this is this radial derivative of r e to the I phi, r e to minus I phi at r equals to 1. So I don't know whether to use it as is or to write in some other form. Or maybe it's fine to use it as is, without going to this W bars and so on. So if I now substitute this formula, it will be d in dr of 1 over 4 pi logarithm of 1 minus, so it will be z minus r e to I phi, z bar minus r e to minus I phi, maybe let me use a different angle here to make it consistent with everything. Theta. So, and in the denominator, we have 1 minus ZR e to minus I theta 1 minus Z bar R. Sorry, again, and this R coincides with that R which we used for coordinate Z. So it should be some different letter in big R. Sorry, it is big R. And here it's also big R. Yeah, something of this kind, and now we need to. This is derivative in big R. So now we need to compute all this. There will be 4 terms, like minus R e to. So let me write all these terms in the uniform way. So it will be R e to I theta over R e to I theta minus Z plus R e to minus I theta over R e to minus I theta minus Z bar, and the same contributions from denominator. Okay, so some computation of this kind, and at the moment we put this big R equals to 1. And let us also substitute Z equals to R e to I phi. And Z bar equals to R e to minus I phi. Let me check the problem. So if we do this, then so this equality continues here. So this is 1 over 1 minus R e to I phi minus theta. This becomes 1 over 1 minus R e to I theta minus phi. This becomes, well, we can change this sign, plus 1 over, and I also missed the overall factor here, 1 over 4 pi, and here. 1 over 1 minus r e to I and phi minus theta plus 1 over 1 minus r e to I theta minus phi. So, and if we look at okay, it should probably no, I missed the factor of r here, right? No, no, sorry, I missed something. It should be r minus. You should just write this in the numerator, right? I phi minus theta, and here. So we see that this term together, so this term together with this one produces our gain function. So so all this equals to 1 over, so equals to 1/2 gain function of r phi theta plus its complex conjugate. But we see that this gain function is real. It has just some real expression. So it is g of r phi theta. So that's all. We recovered the same expression from this formula that relates different gain functions. Yes, so it was this first problem from the Laplace equation. The second problem is how many questions? Nine. The second problem is what to do when we solve something outside this unit disk, and here I will do absolutely the same. So just write on this formula: u of z bar equals to f0 plus sum from n equals to 1 to infinity fn z bar minus n plus sum from n equals to 1 to infinity f minus n z to minus n. Right, so if you substitute it in terms of this polar coordinates, it will give f0 plus sum of n equals to infinity fn r minus n e to I n phi plus f minus n r to minus n e to minus I n phi. And the absolute value of r is greater than 1. So So if original Fourier series was convergent, if it defines some function, then this series is convergent as well. And this solution is finite when we send z to infinity. So u of infinity equals to f0. And of course, we can also write this again function, but I don't want to do this. It will be just the same expression, but as you see, we should replace z with 1 over z bar. So this gain function simply corresponds to a change in r to r inverse, and everything else is the same. So, so just an analogous problem. And the third problem about some non-trivial conditions at infinity. So usually people do not consider something complicated like some powers of z at infinity because it corresponds to some strange structures. I think the only example is this linear function. So the third problem. So so you have z bar minus some constant z plus z bar should be less than should be finite when z goes to infinity. And we also ask it to vanish on the unit circle. So u of e to I phi, e to minus I phi equals to 0. And there are these conditions. So the naive idea how to solve it is to try to write that u is just a of z plus z bar. Or maybe let us better consider the new function, which is u minus this function. So you can simply write this equation again, that u of z bar minus a z plus z bar is less than infinity at infinity. And the second condition for this function can be written like this: u of e to I phi e to minus I phi minus a e to I phi plus e to minus I phi equals to e to I phi plus e to equals to minus a e to I phi e to minus I phi. So if we shift this function by this linear term, we also shift this boundary condition at the unit circle. So the question is, can we? So this function is finite at infinity, and it has this boundary condition on the unit circle. So can we write this function explicitly? Yes. Mm-hmm. So what will we get using this prescription? Hmm. So we should have such a homomorphic and anti-homomorphic function that their angular dependence is e to I phi and e to minus I phi, and they go to zero at infinity. So what are such functions? So and a reminder that we use this polar coordinates. So it's not a function; it is a times z plus z bar. It can be ambiguously. This function should have this angular dependence when r equals to 1, and it should go to 0 at infinity. And the functions to choose are some powers of z and some powers of z bar. Hmm. And there is also this minus sign. So, yes. Hmm. Yes. 1 over z plus 1 over z bar. So in total, we can write that u of z bar equals to a z minus 1 over z bar plus z bar minus 1 over z. Or in that form, it doesn't matter. So here it is I'm almost sure that it vanishes on the unit circle, because z equals to 1 over z bar, and z bar equals to 1 over z when the absolute value of z is 1. And this problem physically corresponds to a dipole in the external electric field. So this is some potential that goes linearly in the vertical direction. So it's in this problem. Yes, of course. So we can simply write this, how to call them, counter terms. It's simply that such conditions, I think, do not appear in the physical problems, because they will correspond to some non-trivial configuration of a field, electric field, or velocity field at near infinity. But well, in general, of course, it can be done. So, or maybe actually, if there are some non-trivial boundary conditions, No, if it is something in the finite domain, we will need to also to modify this function, which are like 1 over z. But mathematically, of course, if it is some power of z at infinity, it can be cancelled by 1 over z bar to corresponding power at the unit circle. So, okay. Are there any other questions about this? So is it fine for the other, or something is already unclear? So we're basically using the same technique all the time, just to compare this Fourier expansion with a restriction of some function that is defined everywhere, or so inside or outside this unit disk. Okay, let us now switch to these problems for the bar operator. Probably I will not raise that blackboard, but I raise this one. Oh, actually, no. It was better to keep this formula. Maybe I can still. No, I don't want to keep it. Okay, so let's remove 1D. And now we are looking for this function that coincides with f of phi on the unit circle. So the only option to write it is so it will be now just u of z. So the only option to write it is just to write n in z fn fn z to the power n. So this will simply reproduce that series. This is precisely the question, because so I didn't say where this function should be holomorphic. I only said that we can try to define it somehow, and then the result will depend on the initial conditions, as always in the non-well-posed problems. So we only know about the series that it is convergent on the unit circle, because this function f was defined there. But then the question is what is the behavior of this fn's when n goes to plus infinity or to minus infinity? So or homomorphicity. So if this, so if f ends so if f ends are so maybe I'll write it better, fn over fn minus 1 are restricted by some lambda minus 2 power hmm? Less than 1, but I would like to consider the situation when they are restricted by some number that is less than 1, but so lambda minus is greater than 1. This is when n goes to infinity. And the similar condition for n goes to minus infinity. So in this case, f n over fn plus 1 should be less than some lambda plus lambda plus is less than 1. This is n goes to minus infinity. So if this holds, then this function u will be analytic in the annulus. Absolute value of z is greater than lambda plus and less than lambda minus. This is simply because the series will be convergent in this domain. So it will be some radius lambda plus, and it is lambda minus. And here is the unit circle. And actually, so I don't know if you need to do this rigorously, but maybe at some moment either it should be done or it was already done in the complex analysis. So the statement, so there is the inverse statement that if some function is analytic in such kind of annulus, then it has Lorentz series representation in this domain. And so maybe I can write some simple proof. So, and this way we check that the Lorentz series sums to some analytic function because it converges, it does not have poles, and vice versa. If some function is analytic, then it can be expanded into such a Lorentz series. Maybe let us call this some a lambda plus lambda minus. And this, f maybe u. U is given by some series un z to the n. This is so the proof of this statement is simple. We can simply consider the integral of this kind. So that f of z is 1 over 2 pi. And the integral, or 1 over 2 pi I, the integral over the following contour. So dz over dw over w minus z f of w. And the contour is the following. We integrate counterclockwise along this outer circle of radius lambda plus, and clockwise along the internal circle. So these two contours can be changed, and since the only singularity of this function under the integral is w equals to z, it reproduces the left-hand side, right? Sorry. Yes, f was a function defined on this circle. Thank you. Yes. Over both. This integral means a sum of two integrals, so this contour is a sum of two contours. We can kind of connect them to make it just a connected contour. Simply connect. No, why? This function is analytic only in this annulus. It can have singularities both inside and outside, and this is precisely the point. If you have some function which is analytic inside the circle, unit circle, or whatever circle, its Laurent series becomes a Taylor series. It terminates in the negative direction. It only has positive powers. But if there are singularities, then it is the true Laurent series. And okay. So there are some similarities here, and there are some similarities there. So we can only write this integral that encircles the domain where this function is analytic for sure. So it does not have singularities. So we can change this contour to this point z. So we can write that this integral is 1 over 2 pi. 2 pi I integral of dw over w minus z f of w, and this integral is just around z. So, and this contour is equivalent to this one, because we can freely move these contours if the integrand is analytic. And so we can move these contours together everywhere in this domain, so that they collapse. So this transition can be shown like this. So we can move these contours together. So this is integral in both in positive and in negative direction, so these parts collapse. And here we have this integral around the and this integral in the clockwise direction around z, and in the clockwise, again in the counterclockwise direction. So this cancels, and we are left with this integral simply around z. So we have this formula now, and we can write this integral as the sum of two integrals. So as a difference of two integrals, 1 over 2 pi I, integral d integral over the domain w equals to lambda plus dw over w minus z, w minus z u of w minus 1 over 2 pi I integral over the internal circle. Absolute value of w equals to lambda minus dw over w minus z u of w. And then oh, sorry. Yes. Let me switch them back because let me make at least this consistent. Yes, but it should be the same in in all the formulas. So I think this. Thanks. So let's quite irrational use of the blackboard, but let me probably write here. I don't know. So here I will write two expansions of the geometric progression. So if we have an expression 1 over 1 minus q, it can be written in two different ways. So if q is greater than 1, if q is less than 1, then it equals to 1 plus q plus q squared and so on. So it is a sum from n equals to 0 to infinity, q to the n. But there is another question, there is another case when q is less than 1. So in this case, we should rewrite it as 1 as minus 1 q inverse 1 minus q inverse. And when q is greater than 1, it equals to a sum of sum from n equals to 1 to infinity q to minus 1 minus n minus sum from n equals to 1 to infinity q to minus 1 minus n. So maybe better to write absolute value of q is less than 1 or absolute value of q is greater than 1. So these geometric progressions should be summed differently. So, and this is precisely an example of this phenomenon of different Laurent series. One series is one series is written in the case when singularity is outside this circle where we try to write this series. Another series is for the situation when the singularity is inside. So one series is in positive powers of q, another series in negative powers of q. Yes, thank you. Yes. Maybe let me write it as n from 0. Yes. So there are these two different expansions. And so first it is an illustration of this phenomenon. And second, we will use it now to get the Silverman series for any function. Probably I can already erase this. No, here we have this problem, so let us erase some different blackboard. Let us erase this. It's not very useful anyway. Okay, so we have that equality, and we would like to use this formulas for geometric progressions in both integrals. So when we integrate here over the external circle, we can expand it in the variable z over w, because this variable will be less than 1. So these integrals can be written as 1 over 2 pi I, integral over absolute value of w equals to lambda minus dw over so we want to expand it in z over w. So it is w over w, sum from n equals to 0 to infinity, z to the n over w to the n, f of w. And for the other situation, we want to use this opposite expansion. So 1 over 2 pi I, integral over absolute value of w equals to lambda plus dw over w again, and here it will be sum from n equals to minus infinity to minus 1, the n over w to the n, f of w. So we see that these integrals can be computed. I'm writing again f instead of u. So all these integrals with w times u can be computed, and this gives us sum of un's z to the n from n equals to 0 to infinity. Plus sum from n equals to minus infinity to minus 1 un zn. So it is a sum over all integer n's un z zn. And these UNs, all of them, are given by the formula 1 over 2 pi I integral of dw over w to n plus 1 f of w. And here this integral is the same for any contour that is in this analyticity domain of f. So, for example, we can integrate over some w equals to r, and this r is greater than lambda plus, less than lambda minus, or less or equal. So. So we see that the limitations for the application of this trick is the presence of singularities inside F. And in this case, the radius of convergence of the Lorentz series is defined by a position of the first singularity. So. And in our case, we have this function f defined on some circle, and we try to continue it as an analytic function inside this circle and outside this circle. And depending on the initial conditions, this procedure terminates at some radius. And it is very similar to what happened to the Laplace equation with some initial conditions instead of boundary conditions, or not so similar to what happened to the heat equation. This solutions of these equations have some finite ranges of validity. In this case of analyticity. Nevertheless, it is some meaningful problem. It makes sense to ask about the analytic continuation of some function. Well, basically, all functions are defined such that, or almost all functions are defined such that they're already analytic, and we can use this analytic continuation. But maybe sometimes it can be some non-trivial problem. But you see, it is not an algorithmic problem because it does not it cannot work for arbitrary initial conditions. So if you have some function, then you should think how to perform this analytic continuation in this particular case. So, any questions about this? So, no. No, what do you mean? So the problems, so it can be quite relevant what precisely happens at zero, because it can happen that we just don't reach zero. We meet some singularities for some finite values of z. For example, if it is some function like if you live on this circle, like so there is some pole A and some pole B, and we live on a circle less than 1, greater than 1. We live on some circle of radius 1. So we have some function 1 over z minus a, 1 over z minus b. It will have a non-trivial Laurent series because it has singularities inside and singularities outside. So this function will be 1 over z minus a minus 1 over z minus b, 1 over a minus b. And this internal function is expanded in negative powers of z, and this one is expanded in positive powers of z. So it will be 1 over a minus b, sum of from n equals to 0 to infinity, a to the n over z to n plus 1, minus z to the n over b to the n plus 1. So let's some example. But what is the setting? What kind of function do you want to consider?
Just in general, if you consider that domain like in disk, and if and you consider given disk and already understand these coverages are, and you want to do the same proof, okay, for a function that is analytic there.
Well, inside the
You assume you have to say that.
but do you want this function to be analytic in the unit disk or not?
Yes.
But if it is analytic in the unit disk, it tells immediately that half of these coefficients should vanish. So yes. Yes. Mhm. So if a function, and we will actually consider this case in the next point. So suppose that f is analytic inside D. So this second problem. Then we can say immediately that we can apply this theorem about the Laurent expansion and say that f of z is so u is analytic, that u of z is sum from n equals to 0 to infinity, some un's z to the power n. This is given by some Taylor series. And since we are fixing its a real value, a real part on this disk, we can say that u plus u bar equals to 2 f of phi. U of z plus u of z bar, which is u0 plus u0 bar plus sum from n equals to 0 to infinity. Let me maybe write first the equation and then solve it. So we write this condition that u of e to the I phi plus u of e to the I phi bar equals to 2f of phi. And let us write this condition on the unit circle. So mm, let us write first the constant terms u plus u0 plus u0 bar, and then write all other coefficients. So it will be sum from n equals to 1 to infinity e to the I n phi un plus sum from 1 to infinity e to minus I n phi u bar n, and all this should equal to 2 times sum for all n's fn e to the I n phi. So we can now say that this so that this fn's equals to un's f minus n equals to un bar, and as in this function is real, there is a condition relating this fn and f minus n bar, and we basically found all these coefficients, so we can actually continue our function inside the unit disk. So that's all. So we can write, we can just take 1/2 of the coefficients of this series and cover the formula for u. It can also be written in terms of the green function, and there are some names for such formulas, which are actually for the function on the real line. They're called Kramers-Kronig relations, and they are relations that allow to reconstruct the whole analytic function from its real or imaginary part. But mm, I don't want to derive them. But you see, it can be derived in the standard way. Just suppose that you are solving this problem for the arbitrary function. You write these coefficients as in the integral representations, and then just sum the series. So it's doable, but I don't want to undo this. But it says that this problem is, for example, well posed in the sense that if original series was convergent, then this series for smaller absolute values of z is convergent as well.
So the solution of this is u of z equal to the sum
Mhm.
0 to infinity of f and z.
Yes, so it is maybe it contains arbitrary constant plus IC, and because it is not fixed by this condition for the real part, sum from n equals to 1 to infinity, n equals 0 to infinity, probably f n z to the n.
but in this way, when you value when you value it in zero, you you don't get f of zero.
But what is f of 0?
No, f of zero. I mean the zero coefficient of Fourier series of f.
But why do we need to get it? We just fix the real part of. Okay, okay. Yes, you are right. From n equals to 1 to infinity, plus ic plus f plus f0 over 2. F0 bar plus f0. So this one, this way it is fine, right? No. Hmm? But what precisely is wrong?
No, I don't know, but yeah, I mean, from the condition, the one in the first line, you should get that
F0
zero
actually.
plus u0 bar is equal to 2f0.
Mm. Actually, F0, no, but it was correct originally because F0 was real. So, no, it was fine. From n equals to 0 to infinity. But we have 2F0 here. Mm, so, let me think. Mm, probably, yeah, probably actually we should
Maybe
have.
f0 plus that's
Mm,
no, no.
Sorry, there was a coefficient mm, uh, 1/2. There should be coefficient 2 here, right? Plus f0 plus hmm?
It shouldn't be like f0 plus the sum from 0 to infinity of fn z dn.
But then when we take a complex conjugate of this, we have 2 times f0 plus this series for positive exponents plus the series for negative exponents. But here we should get the series multiplied by 2. Mm. So, hmm? So u of z is this. U bar of u of z bar is minus I c plus f0 plus 2 sum n equals to 1 to infinity f n no, let me write f minus n because we know the symmetry. F minus n z bar n. So when we sum them, we get 2 times f0, 2 times this, 2 times this. And it equals to the sum. U of e to the I phi plus u of e to the I phi bar equals to 2 sum over integers. Right? Mhm. Okay. Are there any other questions? Mhm. Okay, so basically, to get this homomorphic function, we need to remove one half of the Fourier terms of f. Mm.
La parte reale della tua soluzione sia quella. E quindi tu sostituisci la parte immaginaria che non cambia niente la soluzione, non la guarda.
Mm. So is it fine? So it's kind of one half of this Fourier series with e to the I phi replaced by z. Now, finally, this third problem about the Riemann-Hilbert problem. So it is written here. Like, we ask for some function that is holomorphic inside and outside in this circle and has some prescribed jump. So again, we say that, and it also vanishes at infinity. So we simply say that I will just present the answer for this function. So mm, mm, when z is greater than 1, as u of z is given. So let us look at this formula. Uh, and there are two terms for this is for z greater than 1, and it should correspond to negative part of this series for f, for negative Fourier modes. So I'm writing here a sum of f minus n from n equals to 1 to infinity, f minus n, z to minus n. And for absolute value of z is less than 1, I write u of z is sum from 0 to infinity minus sum from n equals to 0 to infinity f0 z to the n fn z to the n. Right? So if you now compare this, then we clearly see this f of phi, because hmm? Then because we have difference f of u of u of z which is greater than 1 and u of z which is less than 1.
Okay, so that is like e to the IP plus epsilon. Non plus epsilon is not to the power of e.
It's to the power. It changes absolute value of z. Absolute value of this number is greater than 1. It is outside, and this one is less than 1. It is inside. So if we now restrict this function to the unit circle and compute its difference with this function, the unit circle, on the unit circle, it will precisely recover the formula for f. So, right? And now there is a way to write this formulas in a unified way. Namely, we can look at this expression. So we can write that it is So this lower one. I can write that it is a sum of minus sum from n equals to 0 to infinity, z to the power n over w to power n plus 1 integral dw over 2 pi I absolute value of w equals to 1 f of w. And since this z is less than w, we can compute this sum and get that it is 1 over 2 pi I. So originally it will be 1 over w minus z, and now it becomes z minus w. dw over z minus w, so absolute value of w equals to 1, f of w. So this works for z is less than w. And if you do the same with the upper formula, then you get the same integral. So this is for z less than w. And here you will have sorry, yes, for absolute value of z less than 1. And here we will have the same integral, 1 over 2 pi I, integral of w, absolute value of w equals to 1, the w over z minus w, f of w. So absolute value of z is greater than 1. And if you don't care about such serious solutions, okay. So if you don't care about the series expansion, in principle, we can just present these formulas and say that they solve the Riemann-Hilbert problem. Because if you want to compute the analytic continuation of this function through the contour, we will need to cross this integration contour and pick precisely the value at this pole, which equals to f of w. So transition from this region inside the unit circle to the region outside the unit circle goes like this. Maybe let me write it somewhere else. The C of z is the integral 1 over 2 pi I. Absolute value of w is always 1. dw over z minus w, f of w. So if you compute, so there is this contour w, and there is z. So when we move z from internal region to external one, it transforms like this. If you compute the analytic continuation, we can deform this contour like this, and then we should write it like this, plus value of a residue. So what is written here? Here we have f of f of so where this so here we have a u of uh, e to I phi minus epsilon, and it equals after this analytic continuation uh, mm, to u of e to I phi plus epsilon plus mm, so here we should be careful because residual of this integral is minus 1. So it should be minus f of uh, f of e to I phi. So f of oh, actually, I should have used a different letter for this f because it is f not of phi but of e to the I phi. So sorry. F of f hat of e to the I phi equals to f of phi. So I should have used this notation from the beginning. So it is f hat of e to the I phi. So we get precisely that relation that we wanted. Oh, this jump in this function u appears because we cross the contour. So I don't have time to say about this debug problem. It's kind of 10 minutes, not more, but probably I'll say this next time. But essentially the answer is that this function is the gain function of debug problem. And here, and in the general situation, we should integrate not over some one-dimensional domain, but over a generic domain. So in the general situation, this becomes a double integral over some domain with this function rho. And there will be different coefficients, like 1 over pi instead of 1 over 2 pi I. Okay. And you also see that this problem, essentially the Riemann-Hilbert problem, is well posed because we can, so as long as we can compute this integral, as long as f this jump function is integrable, we can construct some function that is analytic inside and outside. There are also multiplicative modifications of this problem where we have not a difference of two functions, but a ratio of some matrix valued functions. And it produces a lot of interesting things. And it does not have such simple solution. Okay, so do you have any questions about this? Okay, maybe if no, then thanks for your attention. See you the next week.